Inverses and groups. Let M star be a monoid with identity E. An element A in M is called invertible if there is an element B in M such that A star B equals B star A is equal to E. A group is a monoid in which every element is invertible. Groups appear so often in mathematics that it's worth taking the time to explicitly spell out the full definition of a group. So in other words, I'm just going to repeat the definition of a group, but I'm going to spell out all the details without using the word monoid. A group is a pair G star consisting of a set G together with a binary operation star satisfying 1. Associativity. For all x, y, and z in G, x star y star z is equal to x star y star z. 2. Identity. There exists an element E in G such that for all x in G, E star x equals x star E equals x. 3. Inverse. For each x in G, there is y in G such that x star y equals y star x equals E. The statements of associativity, identity, and inverse together form what is known as the group axioms. Axioms are just statements that we are taking to be true. If y in G is an inverse of x in G, we will usually write y equals x with an exponent of -1. That's pronounced y equals x inverse. So x star x inverse equals x inverse star x equals E. Recall that the definition of a binary operation already implies closure. Closure says for all x, y in G, x star y is in G. Some authors will mention closure explicitly instead of using the expression binary operation. A group is commutative or abelian if for all x, y in G, x star y is equal to y star x. Let's look at an example. Is the commutative monoid Z plus a group? Yes. The inverse of any integer k is the integer -k. For example, the inverse of 1 is -1. The inverse of 5 is -5, and so on. Another example. Is the commutative monoid n plus a group? No. For example, the natural number 1 has no inverse in the set of natural numbers. In other words, the equation x plus 1 equals 0 has no solution in the set of natural numbers. Let's try an exercise. Determine if each of the following commutative monoids is a group. Now's a good time to pause the video, try this exercise yourself, and then resume the video to check your answers against mine. Okay, 2z plus. Yes. The identity is 0, and the inverse of 2k is -2k. 2n plus. No. 2 has no additive inverse in 2n. Z together with multiplication. No. 2 has no multiplicative inverse in the set of integers. Power set of A together with union where A is a non-empty set. No. A has no inverse in the power set of A, for example. If B is in the power set of A, then since B is a subset of A union B is equal to A, which is not the empty set. Remember that the empty set is the identity of this commutative monoid. Recall that a rational number is a number of the form a over b, where a and b are integers and b is non-zero. We identify rational numbers a over b and c over d whenever AD is equal to BC. For example, 1/2 and 3/6 represent the same rational number because 1 times 6 is equal to 6 and 2 times 3 is equal to 6. We denote the set of rational numbers by double-struck Q. So we have Q equal to the set of quotients A over B such that A and B are integers and B is not 0. We identify the rational number A over 1 with the integer A. In this way, we have that the set of integers is a subset of the set of rational numbers. We add two rational numbers using the rule A over B plus C over D is equal to A times D plus B times C over B times D. Note that 0 equals 0 over 1 is an identity for the set of rational numbers together with addition. Because A over B plus 0 over 1 is equal to A times 1 plus B times 0 over B times 1, which is A over B. And 0 over 1 plus A over B is equal to 0 times B plus 1 times A over 1 times B, which is also A over B. The set of rational numbers together with addition is a commutative group. We multiply two rational numbers using the rule A over B times C over D equals A times C over B times D. Note that 1 equals 1 over 1 is an identity for the set of rational numbers together with multiplication, because A over B times 1 over 1 is A times 1 over B times 1, which is A over B, and 1 over 1 times A over B is 1 times A over 1 times B, which is also A over B. Now, 0 times A over B is equal to 0 over 1 times A over B, which is 0 times A over 1 times B, which is 0 over B, which is 0. In particular, when we multiply 0 by any rational number, we can never get 1. So 0 is a rational number with no multiplicative inverse. It follows that the set of rationals together with multiplication is not a group. However, 0 is the only rational number without a multiplicative inverse. Q star together with multiplication is a commutative group, where Q star is the set of rational numbers with 0 removed. When multiplying two numbers, we sometimes drop the dot for easier readability. So we might write x dot y as xy. We may also use parentheses instead of dot. For example, we might write A over B times C over D as A over B in parentheses times C over D in parentheses. Whereas we would probably write A times C over B times D as AC over BD. We may even use this simplified notation for arbitrary group operations. So we could write A star B as AB. However, we will avoid doing this if it would lead to confusion. For example, we will not write A plus B as AB. That would just be confusing. Let's try another exercise. Let Q be the set of rational numbers and let Q star be the set of non-zero rational numbers. Go ahead and pause this video, try this exercise yourself, and then resume the video to check your answers against mine. Okay, 1. Explain why Q is closed under addition. Let A over B and C over D be in Q, then that means that A, B, C, and D are in Z, set of integers, and B and D are non-zero. Since the set of integers is closed under multiplication, AD, BC, and BD are all integers. Since the set of integers is closed under addition, AD plus BC is an integer. Since B and D are non-zero, B times D is non-zero. Therefore, A over B plus C over D is equal to AD plus BC over BD is a rational number. Okay, now number 2. Let's explain why Q star is closed under multiplication. Let A over B, C over D be in Q star, then A, B, C, and D are in Z star. They're all non-zero integers. Since Z star is closed under multiplication, AC and BD are both in Z star. Therefore, A over B times C over D is equal to AC over BD is in Q star. Okay, third one. If A over B is in Q, then what is the additive inverse of A over B? It's negative A over B. And for number 4, if A over B is in Q star, what is the multiplicative inverse of A over B? That's B over A. It's time for another example. Let C12 be the set consisting of the numbers from 1 through 12. We can define clock addition by performing addition the way we do it on a 12-hour clock. Here's a picture of a 12-hour clock. Let's do a couple of computations. 3 plus 5 is equal to 8, right? Because if it's 3 o'clock now, then 5 hours later, it will be 8 o'clock. And 10 plus 3 is equal to 1, because if it's 10 o'clock now, then in 3 hours, it'll be 1 o'clock, right? 10, 11, 12, 1. C12, together with clock addition, is a commutative group with identity 12. It's a bit more natural to name the identity 0 instead of 12, and so we would normally write C12 as the set of numbers from 0 through 11. So I'll just replace that 12 by a 0 on the clock. Note that 1 and 11 are inverses of each other because 1 plus 11 and 11 plus 1 are both equal to 0. Similarly, we have the following pairs of inverses: 2 and 10, 3 and 9, 4 and 8, and 5 and 7. Also, 0 and 6 are each their own inverse. We can consider addition on the 5-hour clock. C5 equals the set consisting of 0, 1, 2, 3, and 4. Here's a picture of a 5-hour clock. For example, 2 plus 3 is 0, and 3 plus 4 is 2. C5, together with addition, is a commutative group with identity 0. We have the following inverse pairs: 1 and 4, and 2 and 3. Also, 0 is its own inverse. More generally, for each positive integer n, we can let C sub n be the set of 0 through n minus 1, and we define addition on C sub n as if we were adding on an n-hour clock. C sub n together with addition is always a commutative group with identity 0. If k is between 1 and n minus 1 inclusive, then the inverse of k is n minus k, right? Because when we add k plus n minus k, we get n, which is the same thing as 0 on the clock. The inverse of 0 is 0. We can also define clock multiplication on Cn, the set of 0 through n minus 1, as repeated addition. For example, on C12, we have 2 times 5 is equal to 5 plus 5, which is 10. As another example, 3 times 7 is equal to 7 plus 7 plus 7, which is 2 plus 7, right? Because 7 plus 7 is 2 on a 12-hour clock, and 2 plus 7 is 9. We can also perform this last computation by multiplying 3 and 7 as we would normally to get 3 times 7 equals 21, and then subtracting 12, because we're on a 12-hour clock, to get 21 minus 12 equal to 9. Notice we get the same answer. We can subtract 12 as many times as we need to until we get a number between 0 and 11 inclusive. For example, 5 times 8 is equal to 40, and subtracting 12 3 times from 40 gives us a result of 40 minus 36. Right, the 36 is because 12 times 3 is 36, and we get 4. So 5 times 8 is equal to 4 on a 12-hour clock. We can also perform this computation more quickly by taking the remainder upon dividing 40 by 12. Indeed, 12 goes into 40 3 times with a remainder of 4. Cn, together with multiplication, where Cn, as usual, is the set of 0 through n minus 1, and we define clock multiplication as repeated addition, this gives us a commutative monoid with identity 1. However, for each n in z plus with n greater than 1, Cn together with multiplication is not a group. After all, for each k in Cn, we have 0 times k is equal to 0, which is not equal to 1, and therefore 0 is not invertible. For some values of n, if we remove 0 from Cn, we will get a group, and sometimes we will not. For example, C3 minus 0 together with clock multiplication, or the set consisting of 1 and 2, together with clock multiplication, is a group where the operation is clock multiplication on a 3-hour clock. 1 and 2 are each their own inverses, right? 1 times 1 is 1, and 2 times 2 is 2 plus 2, which is 4, but on a 3-hour clock, that's equal to 1. As another example, C5 with 0 removed, together with clock multiplication, is, well, that's the set consisting of 1, 2, 3, and 4, together with clock multiplication, is a group where we're doing this on a 5-hour clock. 1 and 4 are each their own inverses. 1 times 1 is 1, and 4 times 4 is 16, which is the same as 1 on a 5-hour clock. And 2 and 3 are inverses of each other because 2 times 3 and 3 times 2 are both 6, which is the same as 1 on a 5-hour clock. However, C4 with 0 removed, together with clock multiplication, the set of 1, 2, 3, together with clock multiplication, is not a group. Here the operation is being done on a 4-hour clock. The problem is that 2 times 2 is equal to 0. And so the partial binary operation of clock multiplication is not a binary operation on the set consisting of 1, 2, and 3. Equivalently, the set consisting of 1, 2, and 3 is not closed under clock multiplication on a 4-hour clock. If we delete the offending element 2 from this set, we see that the set consisting of 1 and 3, together with clock multiplication on a 4-hour clock, is a group. Okay, once again, the operation is multiplication on a 4-hour clock. Let's try another exercise. Determine if each of the following is a group. If so, state the inverse of each element. If not, provide a counterexample to show that the inverse property fails. Okay, now's a good time to pause the video, try these problems yourself, and then resume the video to check your answers against mine. Okay, the first one, C6 together with clock addition. Yes, this is a group. The inverse pairs are 0 is paired with itself, 1 and 5, 2 and 4, and 3 is paired with itself. C7 with 0 removed under clock multiplication. Yes, the inverse pairs are 1 is paired with itself, 2 and 4, 3 is paired with 5, and 6 is paired with itself. C10 with 0 removed under clock multiplication. For this one, the answer is no, right? The problem is that 2 times 5 is equal to 0 on a 10-hour clock. So if 2 inverse were to exist, then 5 could be written as 1 times 5, right? And then 1 would be able to be written as 2 inverse times 2 by the inverse property. Then we could use associativity to write 2 inverse times 2 times 5 as 2 inverse times 2 times 5. But 2 times 5 is 0, so we get 2 inverse times 0, which is 0. This would show that 5 would be equal to 0, which is not true. Let's look at another example. Let G be the set consisting of EA and B, where EA and B are distinct, and let G star be a group with identity E. Let's construct the multiplication table for G star. Since E star X is equal to X star E is equal to X for all X in the group, right, because E is an identity, we can easily fill out the first row and the first column of the table, right? In other words, we can just copy the input row to the row corresponding to E, and we could copy the input column to the column corresponding to E to already get 5 of the elements in the table. Next, let's look at the entry corresponding to A star A. I'll denote that with a box with a dot in it, a dotted box. Note that the same element cannot appear twice in any row. Let me give a brief explanation as to why that's true. However, this may be a little confusing, so if you don't understand it or you have a little trouble with it and need some time to work it out, for now you could just accept the fact that the same element cannot appear twice in any row. You don't have to sit and struggle with this explanation if you don't want to, but I'm going to provide it for completeness. So indeed, if X appeared twice in the row corresponding to Y, that would mean that there are elements Z and W with Z not equal to W, such that X star Z is equal to X and Y star W is equal to X. So Y star Z is equal to Y star W. Then we have Z could be written as E star Z, which could be written as Y inverse star Y star Z. We could then use associativity to write that as Y inverse star Y star Z. We could replace the Y star Z with Y star W to get Y inverse star Y star W. Using associativity, we get Y inverse star Y star W, which is E star W using the inverse property, and that's equal to W. So we have that Z is equal to W here, which, they're supposed to be distinct. This contradiction establishes that no element X can appear twice in the same row of a group multiplication table. Similarly, no element can appear twice in the same column of a group multiplication table. The entry labeled with the dotted box must be either E or B because A is already in that row. If it were E, then the final entry in the row would be a B, giving 2 B's in the last column. That's a problem. Therefore, the entry labeled with the dotted box must be B. Since the same element cannot be repeated in any row or column, the rest of the table is now determined. Okay? In the second row, we have an A and a B, so that must be followed by an E. In the second column, we have A, B, so that must be followed by E. And then we could use either the third row or the third column to see we have B, E, followed by A. What we have shown is that if a group with the 3 distinct elements, E, A, and B exists, with E the identity, then the table is determined. It looks like the table shown here. However, we have not shown that this table actually defines a group. We do know that a group with 3 elements exists, namely C3 together with clock addition. If we replace E, A, and B with 0, 1, and 2 respectively, and the operation star with clock addition, we get the table for C3 plus. We have shown that there is essentially just one group of size 3, namely C3 together with clock addition. Any other group with 3 elements will look exactly like this one, except for possibly the names of the elements. In technical terms, we say that any 2 groups of order 3 are isomorphic. The order of a group is just the number of elements in the group. This group is commutative. To see this, we simply observe that entries on opposite sides of the main diagonal are the same. By definition, in a group, each element has at least one inverse. It is natural to ask if a given element in a group can have more than one inverse. As it turns out, this cannot happen. Group fact 1. Let A be in G, then the inverse of A is unique. Group fact 2. To determine if B and G is the inverse of A and G, we need only show that A star B equals E or B star A equals E. We do not need to verify both equations. Let's finish one more exercise. Let G star be a group, let A be in G, and let B and C be not necessarily distinct inverses of A. Go ahead and pause the video, try this exercise, and then resume the video to check your answers against mine. Explain why A star B is equal to E. This is because B is an inverse of A. Number 2, explain why C star A is equal to E. This is because C is an inverse of A. And finally, number 3, use parts 1 and 2 above to show that B is equal to C. Okay, well, we have B equal to E star B using the identity property. And we could write E as C star A from 2. And then we could use associativity to write C star A star B as C star A star B. And then we could replace A star B with E from number 1 to get C star E, and C star E is just equal to C. So we see that we have shown that B is equal to C.